In the previous lecture, when we started the arithmetization process, we've seen that in the end, the set of axioms over a finite language is primitive recursive, or rather the set of Gödel numbers of axioms over a finite language. We can now ask related questions. So, for example, what about the set of validities over a language? The key difference here is, of course, that the set of validities involves the notion of proof. So before we can say anything about it, we have to look at the coding of proofs. Coding proofs is actually not that different from coding formulas and other objects, because proof is just a sequence of formulas, and since every formula is assumed to already have a Gödel number, so we can just assign to each proof a Gödel number or a code by just taking the Gödel numbers of the formulas in the sequence and forming the code or the Gödel number of that. And then doing a careful analysis, just like in the other cases of formulas, terms, sentences, and so on, we can show that the set of proofs, so pure proofs, or the set of pairs, where first is a code for a proof of, and the second is the Gödel number of the formula, and we take all pairs such that the sequence that this number here codes is a proof of the formula with Gödel number here. So that set is primitive recursive. So now as a corollary, we get that the set of validities is recursively enumerable, because we can write it or characterize it as a number n is in val, if and only if, of course, n is a formula, right? And if there exists a y such that this is a proof of, so y codes a proof of the formula with Gödel number n. And since we know that this is recursive, or even primitive recursive, and then this here is a one existential quantifier, so it is in sigma 0, 1 form. That means it is, by the canonical form of RE sets, it is a recursively enumerable set. Of course, we can ask now, is this actually recursive? And this we will answer later on. We can now also include theories into these effectivity or decidability questions. So let T be an L theory. As always in this lesson, we assume that L is a finite language. We say T is recursive if the set of Gödel numbers that are in of sentences that are in T is recursive. T is recursively axiomatizable if there exists a L theory T prime such that the deductive closure with respect to sentences of T prime is the same as the deductive closure of T. So T prime can prove the same things that T can prove, only that T prime has to be recursive. Finally, a theory is decidable if everything, the set of Gödel numbers that are of sentences that are provable from T is recursive. So we'll refer to this set as theorem sub T. And now we can show, similar to the validities, that if T is recursively axiomatizable, then the set theorem sub T is recursively enumerable. And of course, the proof now works similar. First, you will show that the set proof sub T, which would be the set of all pairs of, the first one would be a code of a proof, and the second one the code of a formula, right? So it's that P is a T proof of phi, so that this set is recursive And then you would use this characterization that we also used for validities, namely that n is in theorem sub t if and only if n is in the set of sentences or codes of sentences, and there exists a y such that n y is in proof of t. And again, we have a sigma 1 characterization of the set. In general, we have that the set of theorems of a recursively axiomatizable theory is only Re. And in fact, we will see as part of the incompleteness theorems that for many cases, this will actually be not recursive. However, in the special case where we have a complete theory that is also recursively axiomatizable, we get that T is decidable. So how one prove this? Well, one would simply argue, right, that we would enumerate the theorems of T, or the set of Gödel numbers of theorems of T. And since T is complete, we know that one of phi for every sentence, so we want to know if a sentence sigma is in T or provable from T, one of sigma or not sigma, and precisely one, has to appear in this enumeration here, and we just wait whichever which one shows up first. And once we see one of these, right, sigma or the negation of sigma, we know which one is provable from T. And that's the decision procedure. Here are a few examples of decidable theories. So we start with the theory of dense linear orders. We know that this is complete, and we have seen various ways how we can show that this theory is complete. And of course, it's also finitely axiomatizable. Next, then algebraically closed field of characteristic P. We have also seen that this is complete. And we obtained this completeness via quantifier elimination. We showed quantifier elimination for this for algebraically closed fields, and then we used the fact that there is a canonical algebraically closed field that embeds into any of those particular structure for given characteristics, and to get completeness. In general, quantifier elimination is often used as a first step to show decidability of a theory, because it allows us to reduce the the provability of general sentences to ones that are quantifier free, and often those quantifier free sentences actually can then easily be decided. But it's not true that every quantifier theory with quantifier elimination is decidable. Algebraically closed fields itself are not complete, but you can do a little bit of extra work or use some more facts about algebra from algebra to show that this still is a decidable theory, using, of course, the decidability of these objects here, or these theories. Next, we have the theory of ordered divisible abelian groups. This is also easily seen to be recursively axiomatizable, and in the homework we have seen that this is complete. Next is Pressburg arithmetic. That also is a decidable theory, and it in particular implies that the theory of the integers with plus, just plus and less than, is decidable. And interestingly, if we look at plus and times, however, and instead of just plus and less than, this will become undecidable. as we will see in the Gödel incompleteness theorems. And then finally, there's the theory of the reals with plus times less than. This is the result due to Tarski, and also usually referred to as the Tarski-Seidenberg theorem, that this theory allows for quantifier elimination, and then you can show that this is also a decidable theory. The question that will now guide us through the rest of the class pretty much is whether the theory of the natural numbers over the language of arithmetic is decidable. And the answer will turn out to be no. And this will also give us a kind of a tool to show the undecidability of a whole bunch of other theories by using kind of coding of this theory into other theories.